So finally, I just want to give some examples to show that sets and functions are really ubiquitous in math. They're the basis of almost all mathematical objects. And also some slightly more out there examples to try and stretch your brain a little bit. So let's do that. So for starters, the real numbers is a set, as we have seen. And functions from the real numbers are basically what you study in calculus. So I don't mean, certainly not all functions. In calculus, you study functions that have certain nice properties. But essentially, the things that you're doing in calculus are defined in terms of sets and functions. So that's a basic example. Another pretty basic example, but maybe even slightly more interesting. The Euclidean plane let's write this down in our convenient set builder notation. So it consists of ordered pairs of two real numbers. So we can write it just like that, right? The elements are pairs of numbers, which are any elements of real numbers. So this is a set. And subsets of the plane are what you study in plane geometry. Again, same comment. Certainly you don't consider all subsets, because there are many subsets that are wild and not very easy to control, not very easy to say anything about. But generally, the things that you are studying in plane geometry are subsets of the plane. And for example, you can say, if you're thinking about the symmetries of objects in planar geometry, what is a symmetry? It's essentially a function from the subset to itself. Not just any function, it has to satisfy some properties. But again, you're thinking of these geometric objects as sets, and you're thinking of symmetries as functions. So it's all built on this foundation. Another example, arithmetic operators. This is not probably what you have in mind when you do addition, but this is how addition is defined. And if you go into algebra, abstract algebra, and things like that, you will define more general things, and you will define them in these terms. So arithmetic operators are functions from pairs of numbers. And let's say, we can put the integers here. We could also put rational numbers, real numbers, etc. So an arithmetic operator is a function from pairs of integers to integers. For example, addition takes two integers and spits out a new integer. Multiplication, same thing. Takes two integers and gives you a new integer. So you can think about it as a function. Here are some more examples, which are, these ones are not meant to convince you that they're ubiquitous in math. Hopefully you are already convinced, since they are the basis of calculus and geometry and arithmetic and anything else you could think of. But here are some more examples, just to get a little wild. So for any set A, there is a unique function from the empty set to A. And it is called the empty function. If you're curious about things like vacuous truth, these funny edge cases, I encourage you to think about this. Think about why this is, and maybe like prove that it's unique. And here's an example of phrasing something that I said the other day in terms of these ideas. The derivative is a function from functions from the real numbers to the real numbers, which are differentiable, to more functions. What is this saying? All this is saying is that, what does it mean to take the derivative? It means you take a function, which is differentiable, and the derivative gives you a new function. So you can write it like this. And for example, using some more language we use today, what is the preimage of f of x equals 0? So this is a function that I'm considering to be in this set. You can see that I've drawn the element symbol at a funny angle, just to show that this is an element of that. Maybe that didn't need explaining, but let me just say it. So what is the preimage of this thing? It's an element of the codomain. What is the preimage in the domain? It is the constant functions. And this is a fact that we used in the proof the other day. Again, let me say that I'm not going to assume that you know calculus for any of the, anything that you're going to be graded on, anything that's going to be required for the course. But I want to give examples in terms of calculus, because I think that's something that many of you are familiar with. And we gave this proof the other day that a solution to an initial value problem, if it exists, is unique. And we use this fact that we can state in this way, that the preimage of 0 under this map is the constant functions. In this example, I also encourage you to try and think about, if you're interested in doing any kind of abstract math, because this is the way that math becomes quite abstract and can become quite difficult to understand. Because what you have here is you have a function which has a domain and codomain, which are sets. And the elements of these sets are functions, which have their own domain and codomain, which are these sets. And these sets have their own elements, which are real numbers. So it really can get quite abstract quite quickly when you start defining sets whose elements are functions, and then you define functions between those sets, and then you take sets of those functions. This is the kind of thing that really does happen if you go further into mathematics. So this is going to be an interesting thing to try and wrap your head around.